The primary objective of an acquisition specialist is the absolute, mathematically proven preservation of original digital evidence. IT professionals duplicate data every day to back up servers or migrate user accounts. In a forensic investigation, relying on those standard duplication methods will destroy your case. Look at this standard graphical interface. When an operating system copies a file, it only grabs active, allocated files visible to the user. An operating system is the core software that manages all computer hardware and software resources. Executing this transfer immediately alters crucial metadata. The act of selecting and moving the file updates its access times on the source drive. Relying on standard IT copy methods overwrites timestamps and completely ignores hidden data, actively destroying the digital crime scene. To secure the evidence, investigators perform a physical bitstream duplicate. This is a sector-by-sector physical replication of the storage device executed at the lowest possible data level. This hex editor view illustrates the process. A hex editor is a tool that allows an examiner to view the raw, low-level binary data of a disk. The bitstream duplicate captures all active files, hidden system files, and the empty, unallocated space. Unallocated space holds fragments of previously deleted data. Capturing this space provides a goldmine for investigators attempting to recover intentionally erased files. A flawless bitstream duplicate holds zero legal weight, unless we can mathematically prove to a court that it is an exact, unadulterated replica of the original drive. The forensic pipeline starts with target drive preparation. An examiner cannot copy evidence onto a standard, off-the-shelf blank hard drive. The target drive must be forensically sterilized. This requires wiping the target drive. Wiping means completely overwriting every single sector of the target drive with zeros or random characters. It is a total eradication of data, unlike a quick system format. If remnants of a previous case survive on the target drive, the data becomes commingled. Opposing counsel will use those surviving fragments to discredit the integrity of the current investigation. After wiping, the drive is formatted. For target drives larger than 32 gigabytes, examiners format using the NTFS file system. NTFS is a Windows file system capable of handling massive single forensic image files. A forensically sterile, properly formatted target drive provides the required baseline to defend evidence integrity in a courtroom. The greatest immediate threat to a source drive is the host computer itself. Booting up a Windows machine actively alters data and timestamps on any connected drives. During a static acquisition, where the suspect device is powered down, the primary defense is a hardware write blocker. The write blocker sits between the workstation and suspect drive. Blue read commands pass seamlessly to extract data, but red write commands are physically blocked. This forces a one-way extraction. The source drive is thoroughly cloned without a single bit being altered. A physical hardware write blocker cannot always be used, especially if the drive cannot be safely removed from a suspect's laptop. The alternative is using forensic software boot media, like Mini-WinFE or Kali Linux Live, to start the computer. These specific boot environments are designed with a forensic mode that intentionally mounts all connected drives strictly as read-only. Whether utilizing a hardware bridge or a specialized boot operating system, establishing an absolute read-only data flow is mandatory before initiating the clone. The cloned data must be saved into a specific forensic format. Open-source raw formats create sequential flat files that are fast to write and universally compatible, but they do not compress the data. Advanced Forensic Format, or AFF, and proprietary vendor formats offer lossless compression and integrate vital metadata directly into the image file. Proprietary formats restrict the examiner to specific vendor analysis tools, forcing a choice between built-in features and cross-platform compatibility. The physical environment also dictates the approach. A static acquisition of a powered-down PC is highly controlled, but complex environments force a live acquisition. A live acquisition is required when a suspect system cannot be shut down. The examiner must capture data while the operating system is actively altering files in real time. In enterprise environments, examiners encounter massive storage arrays called RAID systems. RAID stands for Redundant Array of Independent Disks, combining multiple drives into one large volume. For these, examiners use logical or sparse acquisitions. A full physical bitstream duplicate of a multi-terabyte RAID array is physically impossible due to size constraints. Examiners target specific files or active data fragments instead. The acquisition format and scope must adapt to the physical realities and constraints of the target environment. The final stage of the pipeline is cryptographic validation. Hashing algorithms like MD5, SHA-1, and SHA-256 process the entire drive's data to generate a unique hexadecimal value. This string acts as an exact digital fingerprint. This output displays a file comparison command. Hashing algorithms are incredibly sensitive. A microscopic change in the data results in a completely different hash value. Altering a single hidden character breaks the mathematical match. Professional tools calculate the hash of the source drive, then immediately verify it against the newly created image file in real time. If the original source hash and the forensic image hash do not perfectly match, the copy is mathematically invalid and the chain of evidence is broken. Modern hardware actively subverts the traditional rules of a static acquisition. The threat comes from the architecture of solid-state drives, or SSDs. Traditional magnetic disks record data on physical tracks. SSDs rely on an array of NAND flash memory cells. NAND is a specific type of non-volatile storage technology that does not require power to retain data. A hardware write blocker stops the operating system from changing data on the connected drive. It does nothing to stop the SSD from changing itself. Look at this SSD simulation. To prolong the drive's life, a built-in maintenance utility called wear leveling autonomously moves blocks of data from heavily used memory cells into fresh, unused cells. This redistribution occurs in the background, executing independently of the host computer. The drive also utilizes garbage collection and the trim command. Trim communicates with the computer's operating system to locate and permanently erase memory cells containing recently deleted data in the unallocated space. Because trim and wear leveling run autonomously upon power-up, simply turning on a write-blocked SSD to image it alters its unallocated space. The drive effectively erases its own deleted files, changing its original digital fingerprint. Examiners must use strict procedural mitigation strategies when dealing with SSDs to combat this automated background data loss. The acquisition must be performed with extreme speed. In certain cases, examiners may need to completely disable the drive's trim function before securing it in an evidence locker. A mismatched hash on an SSD doesn't automatically ruin a case. The examiner must use their technical expertise to document the mismatch and scientifically explain the hardware's automated behavior to the court. From wiping the target drive to deploying hardware write blockers and executing cryptographic validation, the pipeline exists for one reason. Digital forensics requires the mathematically verified preservation of a specific digital state, defending the truth against a hardware and software ecosystem specifically designed to constantly overwrite it.